Welcome to my 38th tutoring session in A-level chemistry. In this video, I'll talk about dipole moment. Don't forget to subscribe my channel, share, like, comment and watch the full video. Now the concept of dipole moment arises when there is unequal distribution of negatively charged electrons in the molecule. And when this happens, there will be development of partial positive and partial negative charges in the molecule. The molecule tends to develop partial positive and partial negative charges when there is electronegativity difference between the bonding atoms in that particular molecule. And when the electronegativity difference is greater than 0.5, the molecule will be polar in nature. Let me explain the concept of dipole moment with respect to hydrogen chloride molecule. In the hydrogen chloride molecule, you will find that there is unequal sharing of electrons between the hydrogen and the chlorine atom. The shared pair of bonding electrons is more towards the chlorine atom. This is because chlorine atom is more electronegative than hydrogen atom. The chlorine atom has an electronegativity value of 3.1, while the hydrogen atom has a value of 2.1 on the Linus-Pauling electronegativity scale. And therefore, chlorine atom being more electronegative than hydrogen atom, it attracts or pulls the shared pair of bonding electrons closer to itself. And as a result, the chlorine atom, it gains a partial negative charge, while the hydrogen atom gains a partial positive charge. And this is shown by Greek symbol delta. So delta plus and delta minus, meaning partial positive and partial negative charges. So remember, whenever the electronegativity difference between the bonding atoms in a molecule is greater than 0.5, you can take it for granted that the molecule will be polar in nature, or it will be a polar molecule. So here in the case of hydrogen chloride molecule, the electronegativity difference is 1, which is greater than 0.5. Therefore, it will be a polar molecule. The chlorine atom being more electronegative than hydrogen atom, it tends to attract or pull the shared pair of bonding electrons closer to itself, and this is indicated by arrowhead pointing towards chlorine atom. And as an outcome of this, you'll find that there is polarization of the electron cloud in the hydrogen chloride molecule, with the electron density is distorted more towards the electronegative chlorine atom. So the electron density is more towards the electronegative chlorine atom, and as a result, you'll find partial positive charge and partial negative charge in the hydrogen chloride molecule. And dipole moments occur when there is separation of charges, that is positive and negative charges. So now you find the hydrogen chloride molecule. It has a positive end and a negative end. It has a dipole, and this results in a polar covalent bond between hydrogen atom and the chlorine atom. Now dipole moment is represented by an arrow with a crossed end. The crossed end will be the positive end of the molecule, and the arrow end will be the negative end of the molecule. So a polar molecule has a dipole moment. Now, dipole moment is a vector quantity. That is to say, it has both magnitude and direction. It is mathematically represented as mu is equal to q into r, where the Greek letter mu indicates the dipole moment, while q represents the charge and r represents the distance between the charges. So dipole moment indicates the polarity of the molecule, and the polarity of molecules, they are expressed in dBA units. For example, the dipole moment for water is 1.84 dBA units. Now dipole moment is 0 for nonpolar molecules. This is generally seen in case of homoatomic molecules like hydrogen, oxygen and nitrogen. Now in case of homoatomic molecules, you will find bonding between identical atoms with similar electronegativities. So in case of homoatomic molecules, since you find the bonding between identical atoms, the electronegativity difference will always be 0. So dipole moment is 0, and as well as the electronegativity value or the electronegativity difference between the atoms is also 0 in case of homoatomic molecules. So what about heteroatomic molecules? Now in case of heteroatomic molecules like hydrogen chloride, you will find the bonding between different atoms. So when there are different atoms, they'll be having different electronegativity values, and this will lead to electronegativity difference between the dissimilar atoms bonded together. And remember, whenever the electronegativity difference between the bonded atoms is greater than 0.5, it will be a polar molecule, and definitely it will have a dipole moment. Now this is not always the case. There are few exceptions, like in case of carbon tetrachloride molecule. Now carbon tetrachloride is a heteroatomic molecule where you find different atoms bonded together. So here in case of carbon tetrachloride molecule, you find bonding between carbon atom and the chlorine atom. So in the CCl4 molecule, you will find 4 polar carbon chlorine bonds. And as a result, you will find 4 bond dipoles between the carbon and the chlorine atom. And as a result, these 4 carbon chlorine bonds that are similar, they mutually cancel each other. Or you can also say that the carbon chlorine dipole moment vectors, they mutually cancel each other, resulting in net dipole moment of 0. Now similarly, in case of carbon dioxide molecule, so it is also a heteroatomic molecule where you find 2 polar carbon oxygen bonds, and you find 2 carbon oxygen dipoles, and they mutually cancel each other. Or you can say the 2 carbon oxygen dipole moment vectors, they mutually cancel each other, resulting in a net dipole moment of 0. So here is a table depicting the dipole moment values of some important molecules like hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, water, methanol, ethanol and ammonia. So fluorine is the most electronegative element in the periodic table with a value of 4 on the Linus Pauling electronegativity scale. So fluorine is more electronegative than chlorine. Chlorine is more electronegative than bromine. Bromine in turn is more electronegative than iodine. So when you compare and contrast the dipole moment values for all these 4 molecules, you will find that the dipole moment values decrease with the decrease in the electronegativity of the bonded atom. So as the electronegativity of the bond atom decreases, here in the case halogens, you'll see a corresponding decrease in the dipole moment values. And similarly, in case of water molecule, methanol, ethanol, and ammonia. So when you compare and contrast the dipole moment values of these four molecules, again you find there is a decrease in the dipole moment values. So water is more polar than methanol, methanol is more polar than ethanol, and ethanol molecule in turn is more polar than ammonia. So as the polarity of the molecule decreases, you find that there is a corresponding decrease in the dipole moment values. So water is a polar solid. It is a bent molecule due to the presence of two lone pairs of electrons on the oxygen atom. So the two lone pairs of electrons on the oxygen atom, they repel the two bonding electrons or the shared pair of electrons and pushes the two hydrogen atom downwards, resulting in a bent molecule. So it has two polar oxygen hydrogen bonds, and each oxygen hydrogen bond, it has a dipole moment vector with a value of 1.5, and these two dipole moment vectors, they sum up together, resulting in a net molecular dipole value of 1.84 dBA units. So you can also understand this concept with these two important points, that whenever the centers of positive and negative charges coincide, it will result in a non-polar molecule, like in case of carbon dioxide and carbon tetrachloride. And whenever the centers of positive and negative charges do not coincide, it will always be a polar molecule, like in case of water molecule. So in case of water molecule, you will find that the center of the positive charges is not the same as the center of the negative charge. So the center of positive charge and the center of negative charge in case of water molecule is different. They do not coincide, and therefore water molecule is polar in nature. Well, in case of carbon dioxide and carbon tetrachloride, you will find that the center of the positive charge and the center of negative charge is one and the same, and therefore these two are non-polar molecules. And what you see here is the orientation of polar and non-polar molecules under the influence of an electric field. Now you very well know that polar molecule has a positive end and a negative end, and when it comes under the influence of an electric field, they orient themselves, or I can say they line up under the influence of an electric field. While in case of non-polar molecules, they have no effect on the, or you can say the electric field has no effect on the orientation of non-polar molecules. And even in the presence of an applied electric field, these non-polar molecules, they'll be randomly oriented. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.